Alright, welcome back to Magnetic Flux Galore. If you want to check out problem number 3 and 5 and see what's going on with that, check out part 1, but this is going to be part 2, and we're going to be looking at problem number 7. A little bit harder, it's in blue, that means it's spooky, and let's get ready for it. So, a cube of length L is 2.5 centimeters, and so I've taken the liberty of converting that to meters. There's a uniform magnetic field throughout the region that has the following components. So I'm going to write this in component form. And so for those of you who aren't familiar with vectors or the joy that is vector math, component form simply means that I'm going to list this vector because remember, magnetic field is a vector. So this is our x component, this is our y component, and this is our z component. And they give it to you a little bit separately, but it's they both mean the exact same thing. So don't get confused by the notation, but it's just a more compact way of writing it. So we're going to calculate the flux through the shaded face of the cube, which is this guy right here. It's highly helpful if you have the diagram in front of you because I'm no good artist. And we're also going to find the total flux emerging from the volume enclosed by the cube. In other words, the total flux through all 6 faces. That's part B. We'll get to that a little later. So for part A, calculate the flux through the shaded face of the cube. Easy part is the area. I've already taken the liberty of doing that. You square this, and we get a number that we've seen a little bit before, 0.0625 meters squared. That is conceptually the very easy part. The harder part is for this B. So here's our cube here, here's our y-axis, our z-axis, and our x-axis. It looks like I've moved the cube to actually a different octant, meaning like I've pushed it to the other side of the x-axis because the x-axis is here. That doesn't actually change anything in this problem, and I just did it because it's easier to draw, so fight me. Alright, so to calculate the flux through the shaded face of the cube, to calculate this beta perpendicular, we want to find the component of this beta that is going perpendicularly to this plane here. There's an easy way to do this and there's a hard way to do this. The hard way to do it would be to find the total magnitude of beta by taking the square root of the square of its components. That's how you find the magnitude of a vector. And then using sines and tangents to calculate the angle at which it goes into it. And then doing beta times the cosine or sine of theta to find the component that's going perpendicular to it. And that's just a whole mess. And we're not going to do it, because they already give it to us in components. So one of these components, or it could be that a combination of the two, but in this case one of these components is going to be the component we are after, and we will just be able to take that as the perpendicular component. So now's a good chance to pause, even if you weren't sure how to do this problem initially, to try to think of which one of these 3 components we're going to use that will go perpendicular into this square face. Alright, so your second is over, or maybe you had more time if you actually paused. So, this face right here lies in the YZ plane, meaning that this is going perfectly in the Y direction. I'm going to use a different color here. This is going perfectly in the Y direction, and this part here is going perfectly in the Z direction. Meaning that any component of the magnetic field that is in the Y direction is irrelevant because it's going perfectly parallel to the face. No component of the Y, part of the Y component is actually going perpendicular. So the Y component we dismiss because it is all going parallel to the face. It'll kind of look like this if you imagine it rotate a little bit, where the magnetic field is going parallel into the surface. This again, if you watch the first video, is an example of a made-up surface. This cube doesn't actually exist. But you would use this to calculate the magnetic flux if there were something there. The other ones had actual loops of wires. This is a made-up surface. That doesn't affect our math, though. So our y component is meaningless. Our z component is meaningless for the exact same reason. Here's our z component. Because our face is in the yz plane, the z component is perfectly, of the magnetic field, is parallel to our face. And so the z component is meaningless. That means that our beta perpendicular is equal to plus 5 teslas. We just stole that x component because if here's our plane face right here, here is the x-axis, there's our x-axis, that part is going perfectly perpendicular to it. Here's our y-axis, parallel to it. Here's our z-axis, also parallel to it. But our x-axis is going straight into it. That's the only one we care about, and so that's why we have isolated it. I drew my perpendicular sign a little bit wrong. Sorry about that, y'all. It's not beta t, it's beta perpendicular. So, calculating the flux through the shaded face of the cube, we have the component that's perpendicular. Now we just multiply that by the area. Now it's easy peasy. Equals 5 teslas times our area of 0.0625 meters squared gives us, drum roll, 0.0031 teslas meters squared. If you want to do some sig figs, go knock yourself out, but I never worry about that. So that is part A. Cool. And now on to part B. So what is the total flux emerging from the volume enclosed by the cube? This is a conceptual problem. It'll require no math. And if you're remembering number 5, the reason it requires no math is because, spoiler alert, the answer is 0. So, to think about this problem, remember when you're calculating magnetic flux, you have to pick a direction that is positive and a direction that is negative, and that has to be consistent for the entire problem. So, let's consider any direction going this way, roughly speaking, to be positive. And I'm sorry, let me backtrack. So it's per each face. So if it's going from outside into the cube, that is going to be one direction. We'll call going outside in to be positive. We'll call inside out to be negative. So for this face right here, the magnetic field that we already calculated, the magnetic field is going from inside out, and so we just decided that we're going to call that negative. It won't affect our previous problem, don't worry. So we're going to call that negative. So the magnetic field, before it crosses through this face, it is inside the cube, and then once it crosses through this face right here, it then goes outside of the cube. So that means that the magnetic flux for this face is negative. However, it's a cube, so it has a face on the exact opposite side. Here, the magnetic field starts outside the cube and goes into the cube through this face. So the magnetic field starts outside, goes through this face right here, keeps on going through, and then comes out the other end. So through this face, we called that a positive magnetic flux, and so it's going to be a magnetic flux positive of, it'll be this exact same value here. And then on its way out, we called that a negative magnetic flux, and so it's going to cancel out. And so if it cancels out on these two sides, it'll end up canceling out because of the opposite of these two sides here, and the opposite from the last two sides. So, for any cube or any sphere, any closed solid that is going through a uniform magnetic field, the total magnetic flux going through all the surfaces will cancel out, and that will be 0. The cube is a simplified way of showing that, but I could show that with a sphere, or I could show that with a cylinder, because any time that the magnetic field is going into the shape, it's going to go out of it just the same, and it's going to cancel out. On each individual surface, however, there is a magnetic flux. But because each opposite surface cancels out, the total magnetic flux is, drum roll, 0. Alright, I hope you had fun with our 3 problems today. Hope this was helpful, and I'll see you next time.